Let's talk a little bit about crystalline and amorphous polymers. Now, in previous videos, we talked about crystalline versus amorphous solids. Crystalline solids have a very regular pattern. Maybe they look something like this. If you imagine the particles, each of these circles being an atom, an ion, or a molecule. While in an amorphous solid, it's a little bit more irregular. It's still solid, so these things aren't moving past each other like they would in a liquid, but it is an irregular pattern. So this is crystalline and this is amorphous solids generally. Now, the focus of this video is to talk about crystalline and amorphous solids made from polymers. Polymers can actually exist in a spectrum someplace between being crystalline and being amorphous. So just as a review, what is a polymer? Well, a polymer is a molecule that's made up of repeated subunits. So you have a subunit, and then it's bonded to another unit, and another unit. And it makes these molecules, which on a molecular scale are long, made up of these repeating units. And so I can represent them, if I were to zoom out a little bit, as kind of a string-like thing. But just remember, these are made up by these repeating units. Now, in previous videos, we talked about how polymers can be amorphous because these long strings of these repeating units can get all intertwined like this and form this messy ball. And we talked about things like elastomers, where natural rubber is like this, where you can pull on it, and as long as you don't pull too much, it'll get back to this form. But it turns out that these polymers can also align to various degrees and become a little bit more crystalline. For example, even with rubber, if you were to pull on it, it's possible that the individual chains get a little bit more aligned. And then the intermolecular forces between them are going to be a little bit stronger because they are a little bit more aligned. And so this form would be more crystalline, not perfectly crystalline, but more crystalline when you have this alignment. And to just see examples of different polymers that sit on that spectrum, let me draw a spectrum right over here, where at this end, we have something that is very amorphous. And at this end, we have something that is very crystalline. We can see examples from our everyday life. If we focus on plastics, for example, polystyrene, which you might be familiar as foam packaging right over here, this is reasonably amorphous. I'm not going to go into the exact numbers, but let's say we could put it right over here. So this is made up of polymers, repeating units, but they're going to be fairly disordered and something like that. And that's what gives it kind of its softness. That's why it's good as a packaging material. It can absorb jolts. Now, if we go a little bit further down the spectrum, something that is still amorphous but has more of a crystalline nature, you can look at things like plastic water bottles, often known as PET bottles. PET stands for polyethylene terephthalate. Anything like polystyrene, polyethylene, the fact that they start with the words poly is the clue that these are polymers. Polystyrene is made up by a bunch of styrenes in a chain. Polyethylene is made up by a bunch of ethylenes in a chain. And so polyethylenes, depending on which version of you look at it, it's someplace between amorphous and crystalline. For example, it might be someplace over here. And if you want to do further research on it, you can actually look up how crystalline something is, the degree of crystallinity. And you'll see numbers like 30% or 40% crystallinity. And if you want to look at especially plastic polymers that are even more crystalline, you can look at something like Kevlar. And Kevlar depends on the Kevlar you are looking at. It can be someplace in this range here. I'll just put the Kevlar right over there. And if you don't know what Kevlar is used for making things like bulletproof vests. And so the degree of crystallinity, and it's not just the degree of crystallinity, but the degree of crystallinity is how aligned these things are. Kevlar, the polymers are very, very aligned with each other. And so you're able to have these intermolecular forces get reasonably strong. And that's why it is good at stopping bullets. While you would never want packaging foam to stop a bullet for you, but these are all polymers.